Hello class, this is Mr. Coker, and we are covering Chapter 19, the representative elements. So this video will be a quick survey of Chapter 19. Feel free to read it in your textbook. There will be a few homework problems from Chapter 19 before we transition into our next topic, which is going to be thermodynamics, free energy, and entropy. So Chapter 19 is really a survey of the periodic table, although it focuses on the elements from the first two columns and the last six columns. These are the elements we call the representative elements. The representative elements have the most variation in their properties from left to right, the alkali metals, the alkaline earth metals, and then over to the right side where you begin to transition to the nonmetals and the metalloids and nonmetals and the noble gases finally. You get a wide range of properties and chemical reactions from these elements. We will be skipping over in this chapter. We won't be covering the transition metals and the inner transition metals, which are the two rows at the very bottom of the table, and then the transition metals being that middle D block of the table. But we'll be focusing on the S and P block because, frankly, most of the interesting chemistry and most of what we talk about in this course does come from the first two columns and the last six columns, the representative elements. So our survey of the representative elements is going to include all 8 sections, 1A through 8A, and a few of the elements we're actually going to focus in on some of the elements that are very important in chemistry. We see a lot of chemistry that involves hydrogen and phosphorus and oxygen and sulfur, so we'll focus in a little more detail on their chemistry. So first, a survey. Here's a periodic table, and the periodic table has that first column, which we call the alkali metals, on the far left, and then the alkaline earth metals are the second column. We have the transition metals in the middle. We're not covering the transition metals in this video. And then down below, the lanthanides and the actinides are considered the inner transition metals. We'll also not be covering those. Their properties are less variable. There is chemistry involved with them, and we do cover it in this class in other contexts. But for this chapter, we're just focusing on the first two columns and the last six columns on the right. So on the right, we see boron, boron's family, the 3A, the carbon family, 4A, nitrogen's family, 5A, the oxygen family, sometimes known as the chalcogens, 6A. And then we get our halogens, which is a named family with fluorine, chlorine, bromine, iodine. Then we have our noble gases, which are chemically inert and kind of unique from the I often even separate them out from any discussion of metal and nonmetal. They're sort of unique. Metals tend to lose electrons and become positive ions, so metals are easily oxidized. Nonmetals tend to be reduced to negative ions, or nonmetals also share electrons and form covalent bonds. But the noble gases, because of their tendency not to react, really don't fit in either category in my mind. We also have the elements along the black stair step there in the green there area of the table, and those elements that sort of border that separation there are called the semimetals or metalloids, or if you focus on their electrical properties, they're semiconductors. So they're very useful in the computer industry as chip making uses semiconductors. So we're focusing on the two purple side on the left and the brown hydrogen, the green area, and then the two shades of blue there on the far right. That will be the elements we'll be focusing on in this chapter. So representative elements, their properties are determined mainly because their valence electrons are found in S and P orbitals, S and P sublevels. As you recall, the S and P are the only electrons that are really on the outside of the atom. They are the valence electrons. The transition metals, they fill up the d orbitals, but those d orbitals are always one layer below the valence electrons, and so d orbitals chemistries are often not as involved. They can be involved in bonding, but they're less involved in bonding. The transition metals are at the center of the table. So the representative elements are the s and p electrons. Remember, the left two columns are the s block and the right 6 columns are the p block. The lanthanides are the elements that are filling up the 4f orbitals, but by the time you reach 4f, you've already started the 6s, and so the lanthanides are actually putting electrons in orbitals that are 2 layers down from the outside of the atom. The actinides are filling up the 5f, but by the time you started the 5f, you've already put electrons in the 7s, so your valence shell is 7, and you are putting electrons in the 5th shell, and so those are obviously not the outside of the atom. So the lanthanides, actinides, and transition metals are not part of this discussion, just the representative elements, 1A through 8A. Metalloids are going to be elements on either side of that line that separates the metals from the nonmetals. Now, calling it a line, it's really more of a stair step, but they're going to have both metallic and non-metallic properties. So maybe they'll be shiny but brittle, or conduct electricity but not well, not as well as a metal does. Some people call them semi-metals. Examples would be silicon and germanium. Both are useful for making chips or electronic devices because of their ability to control electron flow, because they're not just excellent conductors that let electrons go where they want to, or they're not like most nonmetals that don't let electrons flow at all. The metalloids, because of their ability to control electron flow, it makes them useful for the information that is stored and transferred as data in computer chips. Metallic character, if we think of just how metallic an element is, we see that as you go down a group, electrons are farther and farther from the nucleus, which makes them easier to remove, and so metallic character increases. So the trends in ionization energy would be the ionization energy lowers as you go down a group, which is a trait of being metallic. Electron affinity decreases, so metals don't tend to add electrons. And then electronegativity decreases, so that when metals bond with nonmetals or other metals, their tendency to attract the shared electrons is less than you would see for a typical nonmetal. Lower electronegativities. Lower ionization energies, higher electron affinities, lower electronegativities. That would be what we mean by more metallic character. So to sort of contrast metals and nonmetals, metals are going to form cations or positive ions by losing valence electrons. Nonmetals are going to form anions by gaining electrons. Metals are going to exhibit electron configuration of the noble gas from the preceding periods. So like sodium, number 11, when it loses an electron, its electron configuration will be like neon, which has 10 electrons, but neon is the noble gas in the period above sodium. So sodium's in the 3rd period, neon is the 2nd period noble gas. And so metals, they are going to attain a noble gas configuration, but they're going to get there by losing electrons and going backwards to the row above. Nonmetals, though, they're going to finish filling their electron configuration up to the noble gas. And so fluorine with 9 electrons, it's going to gain 1 electron, become a F-1 fluoride ion, and it's going to then have a neon electron configuration. So it's going to get the gas and the noble gas in the same period by filling up with more electrons, and in contrast with metals that lose electrons and eventually gain a noble gas configuration. So we do see that the higher groups are more different from one row to the next than the lower groups are. We see a lot of difference between group 1A and 2A, and then group 2A and, or I'm sorry, um, row 1 and row 2, and then row 2 and row 3 tend to have more difference than, say, row 4 and row 5. And that's because atomic size is more different as you go down the chart in the top part of the chart than it is in the bottom part of the chart. And so this means that we see more variation in properties between elements in the same group that are at the top of the chart than we do at the bottom of the chart. One example of this would be if you look at group 1A, lithium through francium are all considered to be alkali metals. But we typically don't say hydrogen is an alkali metal. In fact, we call hydrogen a nonmetal and group it with the other nonmetals and say it usually forms covalent bonds, although it can form a positive ion, but it can also form a negative ion. It can be H+1, it can be H-1, it can be hydrogen ion or hydride. So hydrogen is sort of unique. It's in that column, but it doesn't really fit with that column very well. It's more of a nonmetal in a metal column. Hydrogen is a nonmetal, lithium is a very active metal. And the difference is that hydrogen is much smaller than lithium. So as a result of being much smaller, it's less, has a lower tendency to lose electrons and more tendency to share electrons, which makes it more of an, act more like a nonmetal than a metal, even though its electron configuration, having one electron in the s orbital, would make you think it would be a alkali metal. So when you're looking at an element toward the top of the table that doesn't really seem to have similar properties to the one right below it, you can usually tie that to the difference in atomic radius and how a much smaller atom is going to have different properties than a bigger atom. We see that with group 2A. The first element in group 2A is beryllium, and beryllium oxide, being a metal oxide, you would expect it to be basic. However, it's more amphoteric, and which would mean it's kind of in between base and acid, base and acid, as amphoteric. And that's mainly because of the very small size of the beryllium atom compared to the magnesium atom below it. Magnesium oxide is definitely basic because you put magnesium oxide and water together, you get magnesium hydroxide. So beryllium oxide is a little more ambiguous as to what its chemical behavior is going to be. And again, that is because of the atomic size of beryllium compared to magnesium. So the more ionic the bond is between the metal and oxygen, like magnesium oxide that's a more ionic bond, beryllium oxide is less ionic and slightly more covalent bond. That's going to determine whether you have an acidic oxide or a basic oxide. So if your element to oxygen bond is covalent, you tend to have an acid when you add it to water. In other words, it's an acidic oxide. Whereas if your metal to oxygen bond is metallic, or is ionic rather, ionic bond there, you tend to have more basic for that oxide. In group 3A, we see boron's really the only non-metal because right below boron you have aluminum, and aluminum's about as metallic as you get. And so boron's a non-metal, and right below it's sometimes some people call boron a semi-metal. It is found in some semiconductors as part of a compound semiconductor, but and it can be used as a dopant in semiconductors. But aluminum's definitely metallic. We always talk about aluminum as being a metal. It's got all the properties of a metal. And everybody below aluminum, gallium, and all the ones in group 3 are metals. In group 4A, we have carbon, which is definitely a nonmetal, although the graphite form does conduct electricity because it's a unique bonding in the way graphite bonds. Silicon is more brittle and a semiconductor, so it's kind of in between metal and nonmetal, although it's shiny and like a metal. But then below silicon, you start getting into the other elements in group 4, like tin and lead, and they're going to be obviously metallic in their properties. Carbon is different from silicon, though, because carbon is dominated by forming mainly chains of carbon-carbon bonds. Silicon tends to either form silicon-oxygen bonds in silicates or things like quartz, or silicon-silicon bonds if it's purified to make like a silicon crystal, which is used in a semiconducting chip or a electronic chip for electronics. They also have a difference in how they form pi bonds. Carbon actually forms pi bonds rather simply, and silicon does not tend to form pi bonds. Pi bonds being the way you double bond is by overlapping p orbitals. And silicons don't tend to overlap very well, and carbons does. When we get to group 5, we find a lot of differences in the elements, and group 6 also, in that they can bond in different ways. N2 is really the only stable way that we find nitrogen, but phosphorus has many allotropes, or different ways that phosphorus can bond to form larger aggregates like P4 and other arrangements of phosphorus into groups of phosphorus atoms in the pure element form. We have different allotropes which actually have different colors. There's white phosphorus, there's red phosphorus, there's yellow phosphorus, and they have different chemical properties because they bond differently. So there's different allotropes. Oxygen actually has 2 allotropes. It can be a diatomic molecule O2, or it can also form O3, ozone, which is a different form of the element oxygen, which we call the same element in different forms allotropes. Sulfur has various allotropes. The most common one is where sulfur bonds in an 8-member ring. So a ring of sulfur atoms with 8 sulfur atoms in it. But sulfur can also form chains or smaller subsets of sulfur atoms. In group 7, most of your elements are going to be diatomic, like F2 and Cl2 and Br2 and I2. But your tendency to form negative ions, you see an anomaly being something that's a little bit different. Fluorines actually has more difficulty forming a -1 ion than chlorine does. So in the column, chlorine actually has the higher electron affinity. And that's because fluorine is such a small atom that adding an extra electron to it creates more repulsions. There's less room in the 2p cloud than there is in the 3p cloud. So the fluorine has trouble adding an extra electron because of the extra repulsions. So even though fluorine's nucleus should strongly attract another electron and form a -1 ion, and it does, its tendency to do so is actually less than chlorine's. And that has to do with the space in that outer valence shell cloud. We tend to see a larger increase in atomic radius going from the first member of a group to the second than from the second to the third. So we see a more dramatic difference in atomic size at the top of the table than we do as we go on down. Things tend to get more similar as you go down the chart, and more different between the first row and the second row of a particular group. And this is illustrated if you look at this picture here of atomic radii. You can see that hydrogen is very different in atomic size than lithium. Beryllium, Be, is very different than Mg. Mg is, and calcium, though, do not have as much difference in their size. So you can kind of compare size and atomic radius, and that's the main reason why we see such a variation from the first element in a group to the second element in the same group. So which of these would be the larger atom, sodium or chlorine? So obviously from this chart, sodium is a larger atom than chlorine, but chlorine actually has more electrons, 6 more electrons than sodium does. Sodium has 11 and chlorine has 17. So why, with more electrons, doesn't chlorine have a larger size instead of a smaller size? And it actually has to do with the protons. Chlorine has 17 protons to pull the third energy level in with. Sodium only has 11. So nuclear charge would be our reason for why sodium is larger. Lithium or cesium. Obviously, cesium is larger than lithium, 265 versus 152. But here, our main source of difference is the number of energy levels. Lithium has 2 energy levels, cesium has 6. So 6 energy levels, with each new energy level being added generally to the outside of the atom. 6 energy levels is going to be a larger radius than 2 for lithium. If we look at where the elements are found on Earth, oxygen is actually by mass the highest abundant element in the crust, oceans, and atmosphere. We find it in the oceans in the form of H2O. We find it in the crust in both kinds of main types of rocks. The silicates and the carbonates both contain oxygen. We find it in the atmosphere as 21% of the air. O2 is 21% of the atmosphere. So oxygen is the most abundant element. Silicon, which is found in silicate rocks, which are one of the most common forms of rocks, comes in second. Aluminum often is mixed in many different kinds of rocks. Iron is also found in many different kinds of rocks, as are calcium. Sodium, a lot of that is found in the oceans in the form of sodium chloride. But you also get sodium in various clays and minerals and rocks. And so we see that these elements are mainly distributed on Earth in the form of oxygen, silicon, aluminum, and iron, and calcium, and sodium, and potassium. You get less and less as you go down as far as the abundance of these elements. So oxygen, most abundant element. It's in the air as O2, in the ocean as water, in the crust as silicate and carbonate minerals. Silicon second. Silica and silicate minerals, which make up most of your sand and rocks and soil. And then aluminum and iron, found in various, concentrated in various ores. Aluminum ore is bauxite, iron ore maybe hematite, something like that. In the ores, they're combined with other nonmetals, usually oxygen, and so there has to be some process in which you process the ore to purify the aluminum and iron metal from the ores. If we look at the distribution of the elements in our body, oxygen is again at the top, and big part of that is the fact that it's the main component in water, and water is a big part of our body. But it's also found in other tissues besides the water portion of our body. Carbon, we're carbon-based life forms, so carbon is sort of uniquely concentrated at a higher mass percent in human body than it is in carbon's way down there as 0.08% of the Earth's crust, atmosphere, and oceans. So it's a very small percent of the Earth's crust, atmosphere, and oceans, but a large percent, 18% of our body, we are carbon-based life forms. Hydrogen's up there because of, again, being found in water, but also being found in many of the compounds in our body. Nitrogen found in amino acids, calcium found in our bones, phosphorus also found in our bones, and also in other kinds of phosphobilipid bilayers and things like that. Magnesium as a trace element, potassium, sulfur, sodium, these are all found in our bodies as a appreciable amount. Metallurgy is the process of getting a metal out of its ore. So this is one of the oldest forms of chemistry. The processing of metals to make tools and weapons really drove the chemistry of metallurgy much faster than some of the other forms of chemistry. Just man's need for tools and weapons, you know. Metallurgy is finding chemical ways to reduce the positive ions down to zero. So if I want to get the metal aluminum, it's going to be aluminum plus 3 in its ore. I want it to be aluminum 0. So I have to reduce the charge from plus 3 to 0 by adding 3 electrons to the aluminum ion. So I have to find a way to do that chemically. And so that's the chemistry of metallurgy, is what are the techniques that bring the oxidation state of a metal from its cation positive state to an oxidation state of 0, which is what all pure metals are. So if you ever see a pure metal, like a piece of iron or a piece of aluminum or a piece of copper, and it's the pure metal, it's not some corrosion on the metal, it's not some metal ore, it's the pure metal form, the shiny metal that conducts electricity. That form of a metal always has 0 charge. So there's a variety of reducing agents. You can heat it with carbon, which is common for like iron. Reducing of iron is you heat it with carbon. That's a pretty cheap way of metallurgy. A more expensive way, because of its energy use, is electrolysis, which is actually what you have to do if you want to produce the pure alkali metals, or if you want to produce aluminum. They're more difficult to reduce. Many of the pure elements can be, or not many, but some of the pure elements can be created from the atmosphere. You can, for example, you can get liquid nitrogen, liquid oxygen in pure form by cooling the air and causing it to liquefy. So it's sort of it's like distillation, but you don't have to heat the liquid to evaporate it and then cool it to condense it. You just have to take the gas in the atmosphere and condense it, and different elements will condense at different temperatures, so you can separate it into its pure element form that way. So if you think about the oxygen in an oxygen tank, it may have been made from the atmosphere by simply cooling the air down to turn the oxygen into a liquid at a different temperature than nitrogen liquefies. Air is typically cooled by expanding the air, expanding the gas, because expanding a gas cools. And so by going through a variety of steps of cooling it, and then using the difference in temperature, and then cooling again and again by compressing and expanding and compressing and expanding, you can actually, through a cycle, get it down cold enough to liquefy the air. Okay, so our start from left to right across the table starts with group 1A. These are the alkali metals. Hydrogen is really not considered an alkali metal, but lithium, sodium, potassium, rubidium, cesium, francium. These all have S1 as their valence electron configuration. So lithium would be 2s1, hydrogen would be 1s1, sodium would be 3s1, and so on. We typically say that the alkali metals are soft silvery metals that react violently with water. And when they react violently, it means it makes hydrogen, and the hydrogen is explosive. So hydrogen would be the only one that's not really a very active metal that loses its valence electrons readily. The others would all be considered very active metals that lose their valence electrons readily. They react vigorously with water. They release hydrogen gas, and the heat of the reaction often ignites the hydrogen gas to give you explosions. And so that's, everybody wants to see, let's put sodium in water, let's put potassium in water. What would it look like if I put cesium in water? It's a very popular demonstration reaction. Alkali metals ions are often important in biology, like your sodium and potassium balance in body cells and fluids. And so the amount of potassium and the amount of sodium in your body can really affect the way that nerves and muscles work in your body. So sources and methods for making pure alkali metals. Lithium can be made from electrolysis of molten lithium chloride. So often you take salts from ocean water and then purify them down and make lithium. So it's very important right now in industry because the lithium batteries are using so much lithium, and so finding ways to get that lithium in its pure metal form, very important. Sodium, once again, electrolysis of molten sodium chloride. Electrolysis meaning pass electricity through melted sodium chloride, and at one electrode you'll get sodium, at another you'll get chlorine. And we'll talk about electrolysis before the end of this semester. We'll have a section on that. Electrolysis of molten potassium chloride, and then reduction of hydroxides for rubidium and cesium hydroxide to make the pure rubidium or the pure cesium. Some physical properties. We find that lithium has the highest ionization energy and cesium the lowest. Lithium's a smaller atom, cesium's a bigger atom, so it's easier to take electrons away from cesium. Reduction potential, which has to do with its electrical properties, which we'll get back to when we talk about electrolysis and electrochemistry. The radius of the +1 ion, notice how small it is for lithium, which means Li plus can form very strong ionic bonds. And melting point. We find that lithium has the higher melting point. The smaller atoms mean that the valence electrons can bond more tightly smaller atoms, and it all comes back to Coulomb's law and distances and distribution of electron cloud for lithium versus sodium. In sodium, the electron cloud's more spread out, and so the valence electrons are less capable of holding it in solid metal structure as a solid, so it's more easily melted as you go down the chart. And here we see some typical reactions that alkali metals can have. They can react with halogen, they can react with oxygen, a couple different ways they can react with oxygen to make oxides or peroxides. They can react with sulfur, they can react with nitrogen to make nitrides, phosphorus, hydrogen to make hydrides. Actually, when alkali metal reacts with hydrogen, the hydrogen does not become +1. The hydrogen becomes a -1 ion called a hydride. We always think from acid and base chemistry of hydrogen as a +1 ion, but hydrogen can become a -1 ion with a very low electronegativity metal, which has even a lower electronegativity than it, which will be the positive. It can react with water, and that can be a violent reaction because the hydrogen can ignite. It's even more violent if it reacts with an acid. The metal reacts with H+, it becomes the ion and H2 gas. And so acids are even more violent with alkali metals than alkali metals with water. Now, uniquely, hydrogen's different than most of the alkali metals in its column. It's a colorless, odorless gas, where all the others are solid metals. Hydrogen, instead of forming a metallic crystal, forms H2 molecules under normal conditions of temperature and pressure. Those H2 molecules are not very attracted to each other. They would have to be held together by London dispersion forces, and those are very weak when you have fewer electrons. And so H2 has a very low boiling point and a very low melting point, nearly as low as absolute zero, -273. So it's nonpolar, and its low molar mass means it's not very polarizable. Highly flammable, so you could get 18% air, up to 60% air composed of hydrogen, 18% hydrogen, 60% hydrogen. Those would be considered highly explosive. They would explode if you sparked or lit them with a flame. Hydrogen is often formed from methane or natural gas. If you heat natural gas and water together at high pressure with a catalyst, you can get carbon monoxide and hydrogen. That's one method of producing hydrogen. It can also be produced as you break down hydrocarbons. Typical crude oil does not have very much gasoline as it's in the mixture. You separate crude oil down into different size molecules. The sizes that are gasoline are actually a lower amount of the crude oil than you really want. You want more gasoline and less of the other fractions of crude oil. So one typical process of getting more gasoline out of a barrel of crude oil is to crack the larger molecules in half to make smaller molecules of the gasoline variety. That cracking process can often form hydrogen as a byproduct. And so hydrogen gas is found in various forms and uses by these two methods. One way that hydrogen tends to get used then is to produce ammonia. Remember, production of ammonia in the Haber process is nitrogen plus hydrogen to make ammonia. Of course, N2 is fairly easily formed. You can just get that one from liquefaction of air because nitrogen is 78% of air. But N2 plus H2, where do you get your H2 from? You could split water with electrolysis, or you can get it from one of these two methods industrially, from methane or from gasoline production. Another method of using hydrogen is to hydrogenate oils. Check your margarine jar or tub or whatever, and you're going to find it contains hydrogenated vegetable oil or some other form of hydrogenated oil. Unsaturated oils, and oils tend to be unsaturated because oils are those liquid fats. They're liquid because of their unsaturation, because of their double bonding. Double bonding is what we mean by unsaturated. Double bonded carbon chains are unsaturated, but if you add H2 to that double bond, you'll break the double bond, make it a single, and that hydrogenates it, and that's how you take a liquid vegetable oil and turn it into a solid like margarine, is by hydrogenating those carbon-carbon double bonds to make them single bonds. So hydrogen's usually classed with the nonmetals because it tends to be covalent when it bonds with other nonmetals. It will form salt with active metals also, so it can be covalently bonded or it can be a -1 ion like we saw earlier with lithium. So that's really the typical way we see hydrogen, is either as a covalently bonded nonmetal or as a -1 nonmetal ion with active metals. We call those hydrides. They're binary compounds that contain hydrogen as the negative ion and some active metal as the positive ion. So they're sort of salt-like, like NaCl, except it's NaH. And they're formed when hydrogen combines with most active metals. They're covalent hydrides are when hydrogen combines with nonmetals like oxygen or sulfur, H2S, H2O. Your metallic hydrides are when transition metals are treated with hydrogen gas. And in that case, the hydrogen really doesn't bond to the metal atoms typically in a ionic way. What happens is the hydrogen gets in between the atoms of the metal, and so you actually get interstitial hydrides, and that you can get that when hydrogen gas is sort of penetrates into a transition metal crystal. Transition metals being larger atoms, they've got more space between their atoms. Hydrogen can fit in between those, and so you can get these metallic interstitial hydrides. It's actually one way to sort of store hydrogen safely. You think of hydrogen gas under pressure in a hydrogen vehicle. Well, that's sort of dangerous because you've got this flammable gas under pressure in a big tank in a collision, if that tank is pierced, you've got a hydrogen potential explosion. So one way to maybe take hydrogen in a vehicle and then release it and burn it in the engine would be to store the hydrogen in some kind of transition metal crystal, and then maybe by heating or warming it, you could get the hydrogen to release and become available for the engine. Typically, your hydride ion is going to be -1. The hydride ion is an extremely strong reducing agent. It loves to give that -1 electron to anything it can give it to so it can go back to its more stable form of H2. And so what you can do with hydrides in water is you typically are going to get that hydrogen and then the hydroxide ion, which is similar to an active metal in water, but even more so, even more violent reaction if you take a hydride of an active metal and put it with water. It's very basic and also gives off a lot of hydrogen gas. Of course, your most important covalent hydride is going to be water, H2O. That's a covalent hydride because hydrogen is attached to oxygen, which is covalently bonded instead of the hydride -1 ion that we saw with the active metals. Its polarity and its ability to form hydrogen bonding in the liquid state gives it a lot of unusual properties. It's got a higher boiling point than you would expect based on its molar mass being a very small molecule. You wouldn't expect it to boil at a higher temperature, and it does. It's got a very large heat of vaporization, which means turning from liquid to gas requires a lot of energy to break those intermolecular forces. It has a large heat capacity, has ability to store heat very well as it warms. It's very efficient at storing heat, a large heat capacity. In the liquid state, it's actually more dense than the solid, which is sort of unique. The open structure of ice is the reason for that, because ice forms more of like a honeycomb crystal structure with a lot of empty space in it. It's actually less dense, so ice floats on water. And it's very important for life because its ability to dissolve ionic and polar covalent materials gives it the ability to move nutrients and plants and animals, the ability to circulate the nutrients to the cells. It's very important for life processes. When transition metal crystals are treated with hydrogen, the hydrogen molecules can actually break apart at the metal surface, and the small hydrogen atoms can migrate into the crystal structures, into holes between the atoms of the metal. And so in a way, it's more like a solid solution than a true compound. And if you heat it, you can remove that hydrogen as hydrogen gas. So it's actually a way you could store hydrogen in a solid form, which is very interesting to scientists that are trying to design hydrogen cars. Okay, group 2A. So we're moving our way left to right. Group 2A, we have our group 2A elements. This would be the alkaline earth elements, earth metals, beryllium through radium. They have an S2 electron arrangement. So to gain electrons, they'd have to start the P sublevel, so they don't really want to do that. So instead, they might lose these 2 electrons to form +2 cations. Typically tend to be basic oxides because they are metal oxides. The exception being beryllium oxide does have some acidic properties, so we said earlier it's amphoteric. So here would be, if you're interested in making these pure elements, these are some of their properties and how you would use electrolysis. Electrolysis would be the way to make these elements from their compounds. Usually the chloride form of the compound is what you start with, and then you pass electricity through it to get the pure metal. These also react with water in a similar reaction to the alkali metals. It's just less vigorous. You can, as we saw earlier in first semester, calcium and water will make hydrogen gas. Typically the hydrogen doesn't ignite, but it will make hydrogen gas. Your beryllium and your magnesium metal, much less observable. You can heat magnesium and it will react with water to make hydrogen gas in this reaction above. But room temperature water is really, really slow. So this would be an example of various reactions you might see with the alkaline earth metals. React with halogen, react with oxygen, react with sulfur, react with various nonmetals to make ionic compounds, react with hydrogen, and react with water, react with acids, H+, react with hydroxides. Beryllium actually react with hydroxides, which is unique. Typically metals react with acids, but not hydroxides. So some practical importance to these. Calcium, of course, very important in the structural, as a structural mineral for bones and teeth, and also for other processes in the body. Magnesium plays a vital role in metabolism and muscle function. If you alloy magnesium with aluminum, you get a fairly low density and high strength or moderate strength metal. So it's a way to get more strength with less mass, which is one of the reasons why magnesium and aluminum tend to get used in various processes. If you remember, typically back in the 70s, the muscle cars would often replace the steel rims of the car with magnesium alloy rims. They called them mag wheels. Mag for magnesium, and these were considered very fancy wheels, very cool looking wheels, but they're also practical in that by making the rims of the tires have less mass but not losing strength, you could actually lower the mass, which could speed up the car and give you more speed because you're accelerating less mass. Calcium and magnesium also play a large role in hardness of water. If you say that water is hard water, what it means is it has large concentrations of calcium and magnesium ions. One way to remove calcium and magnesium from hard water is an ion exchange resin, which is a large polymer that has many ionic sites. And when the hard water goes over that resin, the calcium and the magnesium ions bind to those sites. But as those positive ions bind to the sites, 2 sodium ions are released, and that's why you use salt in ion exchange water softeners. You have to pour in salt because at some point you have to cycle that calcium magnesium back out of the resin because the resin gets full, and you have to flood it with sodium ions to get those calciums and magnesiums to release during a cycling phase of that softener where you get rid of the calcium and magnesium. And so that's why you have to pour salt into a water softener, so those sodium ions from the salt. So it's really an ion exchange. You're exchanging sodium for calcium and magnesium, and later you're putting sodium back on and getting the calcium magnesium off. So this is just kind of a schematic of how the hard water turns the water soft by using this resin. Sodium in water does not create the problems with soap and soap scum and hard water deposits. You don't get those with sodium in water like you do with magnesium and calcium in water. Okay, our group 3A elements. So now we're over in the P part of the table. This would be the boron family, group 3A. These are S2, but they also have P1. They have a P electron. These are going to show increase in metallic character going down the group. As you get bigger atoms, the electrons are more easily removed. And so like aluminum is a +3 ion, gallium would be a +3 ion. So here we have our typical comparison of the radius and the ionization energy and the how you would source these elements in nature, and then how you would prepare them by, as we see here, electrolysis is the most common, although boron can be prepared by reduction with either magnesium or H2 gas, but usually it's electrolysis or reduction with hydrogen that we use to get these metals from their various ores that they begin with. So boron is actually typically a nonmetal. It has some unique chemistry in its ability to bond to hydrogen to make boranes. These are actually electron deficient, which gives them high reactivity. So oxygen reacts with them very exothermically, meaning a lot of heat is given off when boranes react with oxygen. B2H6 is a typical borane. The terminal BH bonds are normal, but the bonds bridging between the borons are very unique in that you have, these would be one of the only cases where hydrogen bonds to two atoms at once. So you see here the hydrogens bonding to two borons. You never see hydrogen bond twice, but they can, in the form of boranes, bond to two boron atoms at once. I always say hydrogen is always a branch, never a bridge, but here's actually a case where it does bridge, the exception to the rule. Aluminum, we typically say aluminum's a metal. It's right there on the border between metals and nonmetals, but it's definitely a metal. It's got a high ability to conduct heat and electricity. It's very shiny. It's got a lustrous appearance, although it will form some covalent bonds with nonmetals. We see for aluminum oxide, and aluminum oxide can form acids or react with acids or bases. It's amphoteric. The acidity of the aluminum ion in water is sort of an example of the aluminum forming some covalent-like bonds with water. So it's definitely a metal, but you know it's got some ways in which it sort of crosses the nonmetal into nonmetal as well. Gallium's really interesting. It's got a really low melting point. Your body temperature can melt gallium, which is rather unusual for a metal to be able to be easily liquefied like that. It actually does have a really high boiling point, though, of 2400 Celsius. Gallium can be used in thermometers just like mercury can. So in high temperature thermometers, it's a useful metal because its ability to change density with temperature gives it the ability to move up and down a glass column. Gallium is one of the weird ones like water. It expands when it freezes. So gallium is another example like water of something that expands when it freezes. Indium and thallium, these are less commonly discussed in chemistry, but their chemistry is very similar to aluminum and gallium. They typically not only form +3 ions, but they can lose their 1p electron to form a +1 ion. Thallium, completely metallic in its chemistry. So typical of the group 3 reactions, halogens, oxygens, sulfur, nitrogen, acids, hydroxides. These metals will react with hydroxide, at least aluminum and gallium will. Okay, moving on to group 4. Group 4 chemistry, a lot of carbon and silicon being very important in this family here. Carbon being the nature of life, and silicon being the nature of the inorganic world, the silicates, minerals that are found in rocks all over the earth. So these have an S2P2 electron arrangement. Here's our chart comparing electronegativities and melting points and boiling points and what the sources would be for these elements. Carbon can be found in pure form as coal or diamond, or in compound form in petroleum. Silicon is typically made from minerals that contain the silicon, which are then reduced. Germanium found in ore called germanite. Tin is found in cassiterite. Lead, galena. Galena, Illinois is actually an area where lead was mined. And so these are some ways in which you can prepare these pure elements from their compounds. So at the top of the table and even all the way down to lead, we can form covalent bonds to 4 nonmetal atoms, CH4, SiF4, PbCl4. These would be sp3 hybridized and tetrahedrally arranged. Carbon is unique in its family and its ability to form pi bonds. And carbon can bond in various allotropes, graphite, diamond, fullerenes, which are those sphere-shaped molecules of carbon. Silicon is a semi-metal or semiconductor, typically found in a very high quantity out in nature in the form of rocks as silica or silicates. Germanium is a fairly rare metal, but a rare semi-metal, but it's used in semiconductors and transistors and other electronic devices. Tin, as we know, is often found in thin sheets, tin metal. A lot of uses of tin have been replaced with aluminum. So you might hear an older person call aluminum foil tin foil, because the use of aluminum foil to wrap foods with, people used to use tin for that, because tin could also be rolled into thin sheets, but aluminum was cheaper, and so they transitioned to aluminum foil. You might have galvanized steel on a roof, but people say it's a tin roof. That's because sheets of metal on roofs used to use tin metal, and then iron metal with galvanized with zinc became a cheaper alternative. But people still might use the old word of calling it tin when in fact there's no tin metal in most roofs today, metal roofs. Tin can have different allotropes, white tin, gray tin, and then a form of tin called brittle tin above 161 Celsius. Lead, found in the ore galena, which is lead sulfide, melts at low temperatures, which made it one of the first metals to be made into molds, molded into various materials. It's been around since 3000 BC, although in the past its poisoning effect, because it is a slower process that happens over time, was not really noticed. And so men and women would be exposed to lead, and maybe their plumbing, their lead pipes for their plumbing and so forth. They didn't realize lead poisoning was such a problem. In fact, we didn't stop putting lead in paint until the 1970s, when they stopped using lead in paint, not realizing just how poisoning that lead was. We used to actually have lead in gasoline. There was a anti-knocking agent, tetraethyl lead, that used to be added to gasoline to change the way the gasoline burned and make it burn better. And we were putting lead into the atmosphere, and so children in large cities with lots of gasoline being burned were having large levels of lead in their blood. So lead poisoning was something we've just learned how to avoid in maybe the last 40 or 50 years. So these metals from group 4 tend to react with halogens and oxygen. They'll also react with acids, H+. Our group 5A elements, group 15, Ns2Np3, these actually vary a lot from top to bottom. Nitrogen and phosphorus form -3 ions. Bismuth and antimony are practically metallic, and arsenic is sort of semi-metal. But your metallic character changes a lot from a definite non-metal nitrogen to a definite metal bismuth at the bottom. Different ways to make them. Here we see nitrogen being made from air, liquefying air. Phosphorus is found in various rocks that have phosphorus in them. Arsenic found in some different minerals that have arsenic. Arsenic, very poisonous metal. Arsenic, because of its tendency to mimic nitrogen and phosphorus in the body and then upset the processes of life, arsenic, a very poisonous element. Antimony and bismuth, these are typically formed by roasting, which is heating in air, and then reducing with carbon. They're smelted to make the pure metals, much like iron is. When you look at the elements in this group 5, nitrogen tends to make 3 single bonds, and but phosphorus and arsenic and others can make up to 5 or 6 even covalent bonds by using their d orbitals. And so you can get octahedral or trigonal bipyramidal geometry out of these elements, but you can't with nitrogen, because nitrogen does not have d orbitals. It does not do anything except bond 3 times in a trigonal pyramid form. So typically you get trigonal pyramid for NH3 or NF3, PH3, AsCl3. You get this trigonal pyramid form, but then you can get the trigonal bipyramid form. You just can't do that with nitrogen. We say that the center atom is dsp3 hybridized when it's in its trigonal bipyramid form. And then you can get the octahedral form. Many times these ions can be mixed in ionic structures, the positive being the MX4 plus ion, and then the octahedral form being the minus ion, and then put together they make an ionic crystal. Picking nitrogen out and maybe going into more detail with it, nitrogen N2 has triple bonds which are very hard to break, and that makes nitrogen very unreactive. That's why the atmosphere has consisted of 78% nitrogen for most of the life of our planet here, and not been broken. That triple bond has not been broken. It's thermodynamically and kinetically very stable. It can be formed into compounds, though, at very high temperatures. These compounds tend to then want to go back to the nitrogen form, which means these compounds react thermodynamically in an exothermic way with a negative delta H. And so typically most of your explosives, most of your exothermic reactions in the explosive form are going to be nitrogen-based compounds. So nitroglycerin, C3H5N3O9, if you look at its liquid form, it decomposes into all these gases plus heat. So you can imagine just how explosive nitroglycerin is. You take the very compact liquid form and then let it expand into all these gaseous atoms and give those gases a higher temperature because of the production of energy, because it's exothermic. You can imagine those gases pressure would build up and be very explosive. 4 moles of liquid nitrogen can make 29 moles of gas, plus heat those gases. And so the formation of those hot gases from a liquid state really builds up pressure and can make it very explosive. Nitroglycerin. Another nitrogen-based explosive is TNT, or trinitrotoluene, which is solid at room temperature but decomposes again to make a lot of gases. 2 moles of solid TNT make 20 moles of gases, and energy is again produced. It's exothermic, and that's because forming that N2 triple bond releases a lot of heat. The process of making N2 into nitrogen-containing compounds was very famously, that problem was solved by Haber. He was trying to make nitrogen-based explosives for World War I for Germany, but in effect what he did was he opened up the chemistry to various nitrogen-containing compounds being able to be formed from the N2 in the atmosphere, which really sort of saved our planet from starvation, because NH3, ammonia, is a very important fertilizer for corn and other plants. So this sort of shows how, by getting the equilibrium and the thermodynamics just right, he was able to create a process where hydrogen and nitrogen could be combined to make ammonia at a very efficient way, using catalysts, using temperature, using pressure, using equilibrium constants and so forth. He was able to figure out the chemistry that would be the most efficient for making ammonia from nitrogen and hydrogen. You can get nitrogen compounds coming out of your automobile engine, because your automobile engine is going to bring in air to burn the gasoline, and at the high temperature of that burning gasoline in the combustion chamber inside the engine, you can actually get some nitrogen compounds forming. These tend to be nitrogen-oxygen compounds, which then become pollutants when they get into the atmosphere, because those nitrogen oxides can then be dangerous in the atmosphere. Nitrogen-fixing bacteria, if you know about legumes such as beans and peas and alfalfa, on their root nodules they have places where which these bacteria live, and these bacteria convert nitrogen from the air to ammonia and other nitrogen-containing compounds, which then feed those plants. And so in farming, often the one benefit of planting soybeans one year and corn the next is the soybeans will actually put nitrogen in the soil, which then the corn can use in the next year. Of course, the other reason why is for herbicides, by alternating the broadleaf with the grass, which is the grass form, which is the corn, the broadleaf, and the grasses. You can attack the two main kinds of weeds alternately with the herbicide to use. Denitrification is then when that nitrogen returns to the atmosphere as N2 gas. You lose that nitrogen compound and you return it to the atmosphere as nitrogen gas. That's called denitrification. So the nitrogen cycle in the cycle that then makes nitrogen compounds naturally. So nitrogen cycle in the natural world is that nitrogen in the atmosphere can be turned into nitrogen compounds a couple of ways. One is by lightning. Lightning will convert nitrogen to nitrogen compounds, nitrogen oxides. And so a vigorous lightning storm will actually increase the nitrogen in the soil a slight amount. Or the other way is nitrogen-fixing bacteria. Then when the plants eat, the plant then creates those proteins. Then the animals can then eat the plants, and you get these proteins, these plant and animal proteins that have nitrogen in them. The decaying of those proteins generates urea and ammonia and other nitrogen-based compounds. Various bacteria begin to break these down into nitrites and nitrates, and then denitrifying bacteria convert it back to nitrogen. So you have your nitrogen cycle. Nitrogen hydrides like ammonia. Ammonia is a gas that really burns your lungs, so it's very dangerous. As some people trying to make meth have found out, stealing ammonia from farmers and then getting a big snoot full of that ammonia when they don't have a good way of containing the ammonia. They don't have good containers to transfer the ammonia into, and so they get these big, their lungs burned out by the ammonia because they're trying to steal it. It's mainly used in fertilizers as a way of making corn grow much better. It's got a trigonal pyramid shape and a lot of hydrogen bonding, so a fairly high boiling point compared to the other hydrides in its family. And as we saw back in the acid-base chapter, it's a base because it reacts with water to produce ammonium and hydroxide. So NH3 can form NH4 plus, and those then become the positive ion in salts. So NH4 plus is your one example of nonmetals that mimic a metal. NH4 plus 1, they mimic a metal because they form positive cations. Another form of nitrogen hydrides are hydrazine. So this is similar to NH3, but it's N2H4. And it's also sp3 hybridized and has these lone pairs on the nitrogen. The high boiling point of it shows that it tends to be hydrogen bonded. Hydrazine is used, I believe, for rocket fuel. Powerful reducing agent and used in rocket fuel. Other forms of it you might put a methyl group on it, CH3, in place of one of the hydrogens. So one of the ways in which the U.S. Space Shuttle was propelled was using monomethyl hydrazine. Reaction is self-starting. You mix the fuels and you don't need to spark it. It reacts right away. Got a very low activation energy to react and produces a lot of gases. And those gases, expanding gases, propel the space shuttle upward. Nitrogen is going to form a lot of different kinds of oxides, as you can see on the right. Various reactions with hydrogen, various reactions with oxygens tend to dominate the chemistry of nitrogen. Two nitrogens in one oxygen is something called nitrous oxide or laughing gas, sometimes used as a propellant in whipped cream and other aerosol cans. It absorbs infrared, so it can contribute to global warming and the greenhouse effect. Nitrogen monoxide, nitric oxide, important regulator in biological systems. It's produced by 6 molar nitric acid and copper metal as one of its ways of being produced. And then quickly with oxygen turns into reddish brown NO2. Nitrogen monoxide has a 2.5 bond order based on the fact that it fills the sigma 2s bonding and the sigma 2s antibonding, which those two cancel out, and then the sigma 2p, the pi 2p's, those three are all filled up, but then there's also one electron in the pi 2p star. So instead of having 3 bonds, you only have 2.5 bonds in NO. Its instability means it tends to react to make other compounds like nitrous oxide and nitrogen dioxide, or it can react with oxygen to make all nitrogen dioxide. NO2 can dimerize or combine with itself to make N2O4, and it tends to do this with regularity at room temperature or a little above room temperature. The equilibrium constant decreases with temperature because dimerizing is exothermic, and so it's an example of Le Chatelier's principle. Since heat is given off, the K is going to go down as temperature goes up. Dinitrogen trioxide, that's another form of nitrogen oxide. Dinitrogen pentoxide, so we see nitrogen and oxygen forming a lot of different molecules and ions. NO2 plus, NO3 minus, NO2 minus. We've got a lot of different nitrogen-oxygen possibilities. Nitrogen and oxygen form many different compounds together, some of which are acidic. The Ostwald process converts basic ammonia to nitric acid, which can then be turned into either ammonium nitrate for fertilizer or nitrogen-based explosives. And so that's another process similar to the Haber process, but it's called the Ostwald process. So this goes through the steps of the Ostwald process with heating and catalysts and oxidation with oxygen and dissolving in water, all the different steps by which you can turn basic ammonia to acidic, strongly acidic nitric acid. So that would be an oxyacid. HNO3, you don't want it exposed to sunlight because it decomposes into gases, which can then build up pressure in your container. So nitric acid tends to turn yellow as sunlight shines on it, and that's the NO2 dissolved in the acid that kind of changes its color. Concentrated nitric acid is at its highest solubility level is nearly 16 molar, 15.9 molar. But it's not just acidic, it's also a strong oxidizing agent. So it's got a high tendency to form explosives and supply oxygen to anything that needs to burn. HNO2, on the other hand, another oxyacid, is less acidic. It's actually a weak acid with a Ka of 4 times 10 to the minus 4. With metals, it will form the pale yellow nitrite salt, and which are actually fairly stable. Another element from this family, phosphorus, its ability to form stronger pi bonds than nitrogen and its greater lower electronegativity compared to nitrogen, larger size for phosphorus. Nitrogen forms stronger pi bonds. Nitrogen has greater electronegativity. Nitrogen has a smaller size, but phosphorus can use the d orbitals. This makes phosphorus and nitrogen have some differences in their properties. We talked about the allotropes of phosphorus. One is the tetrahedral P4 molecule, which is white, very toxic form of phosphorus, very reactive. Pyrophoric, it actually can explode on contact with air, catch fire on contact with air. Phosphorus is found in matches. We find that phosphorus has a tendency to give off heat when it reacts with oxygen. So you typically form white phosphorus, you store it under water because you don't want the phosphorus contacting air. Black phosphorus is actually this kind of crystal structure. You can make black phosphorus from either white or red phosphorus, heating it under high pressure. Red phosphorus, you take the P4 units you see in white phosphorus and you chain them together to make the red phosphorus. The red phosphorus is typically the one found in matches. The head of a match has redness to it, and that's red phosphorus. Some matches are made in heaven, others are made in phosphorus factories. Stereoionic substances are going to contain the P-3 anion, like sodium phosphide or calcium phosphide. The P is a -3 ion. And then in the reaction with water, you're going to get the phosphorus to combine with hydrogen to make phosphine, which is analogous to ammonia. Phosphine and ammonia are pH3 and trigonal pyramid. Phosphine is colorless and toxic. So pH3 is a lot like ammonia, but it's a much weaker base, and it's not as soluble in water. Ammonia has bond angles of 107. Phosphine has bond angles of 94, which is a much smaller bond angle for the pH bonds. Phosphorus makes a lot of different oxides with oxygen, with various oxidation states, usually +5 or +3, P4O6 and P4O10. So these have some interesting little cage-like structures you can get by burning P4 with oxygen to make P4O6 and P4O10. You can get these very interesting geometries, cage-like structures to them. Phosphoric acid, H3PO4 or orthophosphoric acid. You get that when you take P4O10 and water and you put them together, you get phosphoric acid, which is a triprotic acid. All three Kas are weak, but the first Ka is larger than the second and the third, as we remember from acid base. Not as good of an oxidizing agent. P406 can also form H2, H3PO4, or diprotic acid as well. So you've got the different forms. So you can also make a monoprotic acid where you only have one H that can be lost, H3PO3. Soluble phosphate fertilizers. Phosphorus is important. It's one of the three letters, KNP. When you look at a fertilizer, bag of fertilizer, you got three numbers on it. One is the potassium, and one is the nitrogen, and one is the phosphorus content of the fertilizer. Phosphate rocks and sulfuric acid are used to make these various phosphate fertilizers that are then put on soil for various plants to grow. Okay, getting over to group 6. Now we're into the oxygen family, NS2P4. So we get the tendency to form -2 ions, -2 anions for O and S and Se. Here's how you would make the various group 6 elements. Typically they're going to form covalent bonds with stuff like hydrogen and halogens. Your heaviest of these group 6 are going to have some metallic properties and lose electrons to form cations, but they're typically not going to lose all 6. So maybe they lose 2 electrons or 4 to make +2 or +4 ions, but not 6. Selenium, one of the members in the group 6. It is found that selenium can actually help with protection from cancer. So they have found a link between selenium levels and cancer. It's also used in the electronic industry because it is a semiconductor. So one benefit to eating walnuts is you're actually putting selenium in your body, which is a protector from cancer. Oxygen, very important element in group 6. It's in the atmosphere as both O2 and O3, oxygen gas and ozone. It's in the soil in the form of oxides, silicates, and carbonates. It's in the water that's in the ocean. It's in the human body, in the water, and a lot of other molecules. So most of our energy is the combination of various fuels, wood and fossil fuels, oil and gasoline and natural gas, with oxygen. So burning with oxygen. That's typically how most energy is made. 21% of your atmosphere is oxygen. In the liquid form, it's a pale blue liquid. It freezes at -219 and boils at -183. But it is paramagnetic. Liquid oxygen is attracted to a magnet, and we talked about that when we talked about molecular orbital model. And so that's part of the magnetism can be explained by the unpaired electrons in the molecular orbital diagram of O2. O3 has 2 resonance structures, so instead of having a double bond and a single bond, it's going to be 2 1.5 bonds. A bond angle of 117 degrees. Trigonal planar, but it's not 120, it's 117 due to the unshared pair repelling the 2 bonds, getting them close together. If you pass electricity through oxygen gas, you get O3. So if you've ever smelled the air after a spark, you're probably getting a whiff of that O3. It's not as stable as oxygen, but if you generate it at a low level in swimming pools and aquariums, it can actually break down wastes in the swimming pool and the aquarium without leaving a toxic residue like chlorine does. So as an oxidizing agent. Some swimming pools will replace chlorine with ozone as its oxidizing agent. The upper atmosphere of the Earth, up in the stratosphere, there is O3, which forms from reactions up in the upper atmosphere. It absorbs ultraviolet light, which helps it to protect us from ultraviolet. And so the ozone hole problem, which happens because chlorine catalyzes the breakdown of ozone, is an issue that we've hopefully warded off the problem by no longer using Freon that releases chlorine into the atmosphere. So back in the 1980s, they changed the way Freon, which is used in air conditioners and refrigerators and freezers, they changed the chemical makeup of those freons so that we would hopefully protect the ozone layer. And we do find that ozone layer is slowly healing over the years since we stopped putting a bunch of chlorine atoms into the atmosphere. Sulfur, another member of group 6, found in nature in large deposits. It kind of comes up from volcanic activity. A lot of the sulfur we have in the United States is made by the Frasch process, and most of that sulfur is then used to make sulfuric acid, which is a very important industrial chemical. So the Frasch process is you recover the sulfur from an underground deposit by pumping superheated water down, melt the sulfur, and the sulfur comes up and can be pumped out. S2 molecules would be sulfur gas. Has stronger sigma bonds than pi bonds, so it's less stable. It's more stable in the form of S6 or S8, or chains of sulfur. Rhombic sulfur is when you stack the S8 rings in a crystal form. Monoclinic sulfur is when rhombic sulfur is melted and heated to 120 Celsius and then is cooled. Here would be some various sulfur chains and rings. You can make sulfur chains up to 10,000 atoms long. Sulfur monoxide would be one of the oxides of sulfur, although sulfur dioxide is a more common one. When you burn sulfur in air and you get that bright blue flame, you're getting SO2. You can smell it. It's a V-shaped molecule, kind of like O3, but a sulfur in the middle instead of an oxygen. Kills bacteria. Sulfur trioxide is when you react sulfur dioxide with oxygen to make sulfur trioxide. Each of the sulfur oxides can be made into acid by reaction with water. They are acidic oxides. Sulfuric acid is a diprotic acid you make when you take sulfur trioxide and react it with water. So that's why burning coal with sulfur in it to make sulfur oxides and then letting those sulfur oxides into the atmosphere where they can mix with cloud water and generate acid rain is such a problem. Sulfuric acid is a strong dehydrating agent. It can remove water from sugar, turn sugar into carbon. You see on there, on the left there, the beaker of sugar, and then you added concentrated sulfuric acid into it. You get this big thing of carbon, and water was released from it. Okay, moving into the halogens, group 7, Ns2np5. So these are going to be dominated either ionically by making -1 ions or the formation of covalent bondings. They're very reactive because of their small size and strong affinity for electrons. They're very reactive. So you're not going to find any of these elements in their pure form in nature. Usually they form -1 ions are found in seawater. The bonds, the single bonds for chlorine's actually stronger than the single bond for fluorine. So kind of fluorine you'd expect to have the strongest, but again, the size of fluorine makes it more difficult to concentrate the electrons to form a bond. Halogens have high electronegativities. They form polar covalent bonds with other nonmetals. So when halogens react with other nonmetals, with maybe the exception being oxygen, the halogen is almost the negative oxidation state, and the other nonmetals are the positive oxidation state. Definitely with metals, halogens are going to be negative and metals are going to be positive. Here's again the description of these elements and how to make them from their compounds. Some of their reactions react with hydrogens to make HX, HF, HCl, HBr. Fairly explosive because the HX bond is stronger typically than the H2 or the X2 bond. Dissolved in water, these are going to be acids, the strongest of which will be HI, and the weakest of which is HF. Here's some of the physical properties of your hydrogen halides, HF, HCl, HBr, HI, melting points, boiling points, bond energies. Notice the strong bond energy of HF makes it more difficult for it to break to form H plus and F minus. So HX is the only weak acid. So it's the only one where we have to calculate the Ka. I'll skip this bottom part with the delta G because we haven't covered delta G yet. We're going to cover that in the next topic. So your acids, probably of your hydrohalic acids, hydrochloric is the most important. Of course, it's stomach acid. It's a very common laboratory acid. It's a very common acid in industry. Hydrofluoric, a lot of chemists use it, but they're very suspicious of it because the HF molecule, being so small, can penetrate through skin and then begin eating away at bone. So unlike other acids that sit on top of your skin and you can wash them off, HF soaks in, which makes it rather pernicious as far as handling it, because if it gets on your skin, you may not be able to get it out. In fact, it gets down into your body, and some people have had to have fingers or hands or stuff amputated because of the effect of hydrofluoric acid on them. But it is used, just used more carefully. Etching glass is one way it's used. And you can make the halogens into various oxyacids, HClO3, HBrO4, things like that. The more oxygens you put in an oxyacid, the more acidic strength. Perchloric acid is your strongest, HClO4. It's not only a strong acid, but it's also an oxidizing agent, so it can be reactive explosively with organic materials because it'll burn those organic materials. Hypochlorous is formed via something called a disproportionation reaction. Disproportionation means that the same element is both oxidized and reduced in the reaction. So we see Cl2 on the left side being 0 oxidation state. HOCl, the Cl is actually +1, and then Cl minus, the Cl is -1. And so the same element, chlorine, goes from 0 and it goes to +1 in one molecule and -1 as an ion. So it's both oxidized and reduced. That's called a disproportionation reaction. Here's your geometry, your valence shell electron pair repulsion geometry for various ions, your hypochlorite, chlorite, chlorate, and perchlorate. We go from linear to bent to trigonal planar to tetrahedral. Fluorine, it's only going to make HOF. It's not going to make anything but HOF as an acid. Oxygen difluoride is another compound of fluorine, OF2. Dioxin difluoride is another way that oxygen and fluorine can bond. That's actually an orange solid. So these would be some various oxyacids that are known with oxygen and hydrogen reacting with the halogens. In an oxidation state all the way up to +7. And finally, we're into our group 8 elements, the noble gases. So these have filled s and p valence orbitals, unreactive. It's only some very few compounds can be made with these elements. S2 for helium, S2p6 for all the other elements. So here's their melting points, their boiling points, how abundant they are in the atmosphere, because that's really where you'd only find them is in the atmosphere as a gas. Although helium can be found as a gas underground because it is a byproduct of alpha decay of radioactive elements. It can actually collect in pockets underground, which you actually drill and pump helium from underground as a way of getting helium gas for your balloons and things like that, or to make liquid helium if you want to have very, very cold reactions. So helium and neon, I think I might have heard that they might have made a neon compound. I can't remember for sure, but they have made compounds with argon, krypton, and xenon. But helium and neon are much more difficult to turn into compounds. Helium's found in natural gas deposits where alpha decay of radioactive elements concentrate helium underground. Doesn't form compounds, but can be used as a coolant because liquid helium gets all the way down to 4 Kelvin as a pressurizing gas, to mix with gases for deep sea diving, for obviously for helium balloons and blimps. Neon, its main use is neon lighting. You pass electricity through neon, you get this nice red-orange glow, which can be used in fancy lights. Argon also used in lighting, but previously, before some of the newer light bulbs, it was used in the incandescent light bulbs because it would prolong the life of the tungsten filament, that little wire that would glow. The argon, because it was unreactive, would not let that tungsten form corrosion on it, which would weaken it. Krypton and xenon form a few stable compounds, but generally are considered low reactivity. So here would be a few reactions, and these reactions of these xenon fluorides will actually generate hydrogen fluoride or hydrofluoric acid. So here would be xenon in various valence shell electron pair repulsion shapes, everything from linear XeF2 to octahedral XeO2F2. Everything in between. It's got xenon can be made in almost any geometric shape. So a little concept check here. Which of the following groups is most reactive? That would probably be the 1A, because the alkali metals tend to react the best of, I would say 1A and 7A are your most reactive groups. Which of the following groups does not contain an element that forms compounds with oxygens? Actually, all of these. Oxygen can make compounds with just about anybody. Certain noble gases, maybe not, but oxygen combines with just about everybody. All right, so we're wrapping up there, and I'm going to put this on Canvas and put a link to this on Canvas and put it on my YouTube channel. So enjoy that.